Okay, picture this. You're running a massive, globally distributed platform. We're talking tens of thousands of microservices, and they all rely on configurations to behave correctly, right? Think feature flags, service level rate limits, kill switches. These aren't just static settings you set and forget. They're actual levers that need to be pulled in real time, safely, and at a scale that's honestly hard to wrap your head around. So, in today's Explainer, we're going to totally unpack the architecture of a global real-time configuration service. We'll explore the exact design you need to handle instantaneous config updates for millions of clients delivered without a single point of failure.
To really get how this works, we have to look at two massive and honestly kind of opposing constraints. The first one is the system's write propagation. When an engineer flips a feature flag or hits a kill switch, that configuration change has to hit every single region globally in under 10 seconds. And within the same region, we're looking at under 2 seconds. So we're talking about near instantaneous global state synchronization. No small feat.
But hold on, because here's the second, and I'd argue even more intense constraint: the read latency. The microservices relying on this platform are going to be making millions of read requests per second. If you introduce even a few milliseconds of network round-trip delay into their hot paths, the entire platform just grinds to a halt. Because of that, the read latency target is sub-microsecond, literally under 1 microsecond. Now, standard centralized database architectures, they instantly fail here. You just can't have clients querying a server. The way data reaches the edge has to be completely rethought from the ground up.
So here's our roadmap for today. First up, the real-time configuration challenge. Then we'll look at the control plane versus data plane. Next is SDK side rule evaluation, followed by solving the thundering herd. And we'll wrap up with versioning and system rollbacks. All right, let's dive right into this with part 1, the real-time configuration challenge.
The fundamental problem we're dealing with here is balancing the need for strict correctness with the reality of chaotic, unpredictable distributed networks. If we look at the exact service-level agreements, the SLAs that this architecture absolutely must meet, you'll see everything anchors to these core numbers. There's that sub-microsecond read latency, the sub-10-second global propagation, and a highly demanding 99.99% availability target. But crucially, look at the maximum stale serve on outage, 5 minutes. Now, this is a massive architectural hint for us. It means eventual consistency is actually acceptable here. In a worst-case network isolation scenario, it's better for a service to run on slightly stale data than to just crash entirely.
Moving on to part 2, control plane versus data plane.
Now, what's really interesting about this setup is how it hits those opposing targets. To get both strong write consistency and massively scalable reads, the architecture actually severs the two paths into a dual-plane setup. The control plane handles the writes. It's low throughput, maybe just a few thousand updates a day, but it requires absolute strong consistency, so it's backed by a durable Raft-replicated etcd cluster as the single source of truth. The data plane, on the other hand, is built for massive scale. Think of it as a regionally deployed caching tier, acting almost like a CDN for the configs, and it uses gRPC, Redis, and a Kafka message bus to get the job done.
Let's trace the exact flow of data for a single config update so you can visualize this. Say an operator updates a kill switch. That write hits the control plane API and is securely saved to etcd. etcd then emits a change event. Next, a propagation service grabs that event and publishes it to a global cross-region Kafka message bus. From there, regional caching nodes, which are basically stateless Go services backed by Redis, subscribe to this bus. The second they see the update, they refresh their local Redis cache and instantly fan out the update via gRPC to all connected client SDKs.
But, things break. What if that push fails? What if the message bus drops a packet or a connection just hiccups? Well, the system relies on a push/pull hybrid model. The push mechanism gives us that blazing fast sub-10-second propagation we need. But every 30 seconds, the SDK performs a lightweight polling heartbeat to reconcile its local cache with the regional node. Basically, this 30-second poll acts as the ultimate safety net. It ensures our global consistency SLA remains incredibly resilient, even if the push pathway completely degrades.
Which brings us to part 3, SDK side rule evaluation. So how exactly do we pull off that magical sub-microsecond read SLA? We do it by shipping a thin, in-process SDK right alongside every single microservice. See, in this system, configs aren't just simple values like a basic string or integer. They are priority-ordered rule sets. For example, if a service asks for the checkout v2 feature flag, the answer isn't just a flat true or false. The SDK actually evaluates filters locally. It checks, is the request coming from the US East region? Is the user a premium user?
And does this specific user fall into the 25% rollout bucket? If none of those conditions match, it just returns the default value.
And this brilliantly illustrates how we handle those percentage rollouts without ever having to talk to a server. The system uses a technique called deterministic hashing. The SDK takes the user ID, applies a mathematical hash to it, and performs a modulo 100 operation. That spits out a clean number between 0 and 99. Now, because the user ID is stable, that user is always going to hash to the exact same bucket. If that bucket number is under 25, boom, they get the feature. It's incredibly fast, perfectly consistent, and completely local. The scale of this is just astounding when you realize it's happening millions of times a second without a single external network dependency.
Honestly, pushing the entire evaluation engine into the SDK's local in-memory hash map is the absolute secret weapon here. It guarantees 0 network calls on the read path, which completely locks in that sub-microsecond latency. It totally eliminates the need for some massive centralized evaluation server that would, without a doubt, become a massive bottleneck. And perhaps the best part, it provides total offline resilience. If the entire config data plane goes down, the client SDK can still correctly evaluate rules based on its cache data. It's a real game changer.
Okay, let's move into part 4, solving the thundering herd. So the system is blazing fast and highly distributed, right? But any senior engineer watching this knows that distributed networks hide some truly terrifying failure modes. I want you to imagine the absolute worst-case scenario. A massive network partition isolates an entire region for 5 whole minutes. Millions of SDKs completely lose connection to their regional nodes. Then, suddenly, the network partition heals. Millions of disconnected SDKs simultaneously rush to reconnect and download the latest configurations. If the architecture isn't explicitly prepared for this, that massive traffic spike will instantly crush the servers. It's the classic thundering herd.
To survive a storm like that, we have to layer in some very specific reliability strategies. First off, the SDK uses a 5-minute stale while serving time to live. This means it doesn't just panic and crash during the outage, it simply keeps serving old data. Second, when the network finally heals, the SDKs use jittered exponential backoff. They don't all try to reconnect at exactly millisecond 0. Instead, they stagger their attempts randomly to spread out the load. But hands down, the most critical layer of defense here is the delta sync.
A delta sync is the ultimate lifesaver for the thundering herd problem. When those millions of SDKs finally do reconnect, they do not download the entire multi-megabyte configuration payload again. Instead, they send a tiny version vector, basically saying, hey, the last thing I saw was version 100. The server looks at the current state, let's say it's at version 105, and it only sends back the specific diffs for those 5 missing versions. This dramatically reduces both bandwidth and CPU utilization during mass reconnect storms. It literally stops the thundering herd dead in its tracks.
Finally, let's wrap up with part 5, versioning and system rollbacks.
Because let's be real, protecting the platform from human error is just as important as pure speed. Bad configurations can and do take down entire companies. So the crucial defense mechanism here is how the data state itself is treated, append-only monotonic versioning. In the etcd control plane, a configuration is never, ever overwritten. Instead, every single change generates a brand new, strictly increasing version number.
Because the whole system is append-only, rollbacks become elegantly simple. Let's say a bad config accidentally gets deployed. First of all, the write was already logged to an immutable audit trail for compliance. Next, because the new version was just appended in etcd, the previous known working version is still sitting right there untouched. When an operator hits the panic button to initiate a rollback, the system doesn't have to scramble to rewrite data. The current version pointer simply shifts atomically back to the previous version number. And then, that pointer update is instantly fanned out across the Kafka bus down to the SDKs. Fast, safe, and clean.
So, this architecture utilizes gRPC streaming, a push-pull hybrid model, deterministic hashing, and append-only versioning to reliably serve millions of reads per second globally. But let's push the boundaries even further. What if sub-microsecond just wasn't fast enough? How would you adapt this exact architecture if your read SLA was constrained strictly to hardware-level CPU caching, requiring sub-nanosecond access? Think about what would actually have to change in the SDK memory model. It's a massive challenge. Thanks for joining me on this explainer, and I'll leave you to ponder that one.